So I am Jane Verana to discuss what is queuing theory together with my partner Miss Eileen Joy Imas. The queuing theory is concerned with studying all the various dynamics of lines or queues and how they may be made to operate more efficiently. It is essentially the study of waiting in line. So let's remember that queuing theory talks about waiting in line, including how people behave when they have to queue up to make a purchase or receive a service, what types of queue organization move people through a line most efficiently, and how many people can a specific queuing arrangement process through the line within a given time frame. So some typical examples of queuing are banks and supermarkets where people in line waiting for service, for computers waiting for a response, and for public transport, people waiting for a train or a bus. So as we know, queues are a common everyday experience. A simple queuing system has a queue where customers stay while they wait for service, and a service facility contains at least one server which performs the service. So here's how it looks. We have here our customer, the color sky blue circle, and our server, the color indigo box. And our service facility are the number of servers. In the diagram, they are the five boxes lined. And in front of the five boxes are some of customers that are being served. And some customers are in the queue or in the waiting line. We consider our system boundary to be including our queue and our service facility and illustrated as well the arriving customer. Since we have different variety of queuing systems, how do we classify different models? With that, we employ the Kendall-Lee notation. This is a six-element classification system in order to categorize different queuing systems. So we have the big letter A, big letter S, small s, big letter D, big letter K, and big letter N. Some examples of different queuing models are MM2 FCFS 2020, DM1 FCFS Infinity Infinity, and GG2 LCFS 100 Infinity. What do these elements mean? For the first element, A represents the arrival process or the input process. This refers to the inter-arrival time of our customers in the queuing system, and we likely let lambda be the arrival rate of customers. The allowed letters for the first element are M for Markovian or exponential inter-arrival time, E sub k for Erlang inter-arrival time, D for constant or degenerate distribution, and G is for any general inter-arrival time distribution. So let's move on for the second element. We have the S for service process or the output process. We let nu as the output rate of our system, which represents the service rate of our queuing system. Similar to the arrival process, we use M for Markovian or exponential, E sub k for Erlang, D for constant or degenerate, G is for any general inter-arrival time distribution. For the third element, small s represents the number of servers in our service facility. Next, our fourth element, the big letter D, which we call queuing discipline. It determines which customers will be served next in our queuing system. The possible entries for the first element are FCFS stands for first come first serve, LCFS stands for last come first serve, SIRO stands for service in random order, and GD stands for any general queuing discipline. And sometimes we include priorities in our queuing system. The fifth element or letter K are called system capacity. This refers to the maximum number of customers that are allowed to enter the queuing system. And last element, we have letter N for input source or calling population. This refers to the number of customers that may enter the system. So take note, if the values of the last three elements, the big letter D, K, and N, are FCFS infinity infinity, we may omit these last three terms. Since we're dealing with the probability distributions in the first two elements of our Kendall-Lee notation, it is a good idea to go over some of the most common distributions in the theory. So we have four distributions, the degenerate or constant, the normal distribution, the Erlang distribution, and the exponential distribution. As shown in the histogram of these distributions based on the increasing variability, we have a fixed value for the degenerate distribution. Meanwhile, we have some variation in the normal distribution and a number of points significantly above the mean when it comes to Erlang, and a high number or a very significant number of large values in the exponential distribution. In queuing theory, degenerate and exponential distributions are more mathematically tractable than normal and Erlang distributions. Degenerate and exponential distributions are used to model simple models. Meanwhile, for some distributions related to normal and Erlang distributions, we don't have many closed formulas. In addition to the histogram from the previous slide, we have some data sets from these distributions here. The degenerate distribution has a fixed value, the normal distribution has few deviations, and the Erlang and exponential distributions have relatively outliers. Therefore, this diagram emphasizes the variability found in these distributions. Another related distribution at the right side picture is called the Poisson distribution. It occurs when the inter-arrival time has exponentially distributed the count of the number of arrivals in particular period, which is said to be Poisson distributed. Let's head on and try to solve the problem using Kendall-Lee notation. Problem 1. A canteen operates an espresso stand. Customers arrive to the stand with an exponential inter-arrival time. The espresso vending machine required exactly 45 seconds for each customer to operate. In this example, we have our customers queuing in a vending machine that serves an espresso coffee. So the arrival is Poisson distributed, and it is known that the service time is constant. So what is the appropriate Kendall-Lee notation for this example? So again, remember our 6-element classification of Kendall-Lee notation. The first element pertains to the input process, and it is Poisson distributed, since the exponential distribution is mentioned already in the problem. Hence, we have Markovian as an input process. For the second element, it pertains to the service time distribution, and in this case, it is constant. Hence, we use D for degenerate. For the third element, we have a single machine. Therefore, we have a single server. That's why we use 1. For the fourth element, we have here the queuing discipline, and we assume a first come first served situation, and that's FCFS. For the fifth element, we have the capacity of the queuing system. So in this case, we don't have a finite capacity, hence we use infinite for the first element. Lastly, for the last element, we have also infinity, since the number of customers that may enter our system is likewise infinite, hence we use infinity as well. Therefore, the Kendall-Lee notation for problem 1 is MD1 FCFS infinity infinity. Again, since the last three elements are observed as FCFS infinity infinity, remember that we may omit these last three elements, so the model can be simply MD1. Another example, students returned books to the library at a rate of 6 books per hour. The borrower's section librarian returns the books one at a time to their respective bookshelves. This takes an Erlang distributed time per book. Since a newly returned book is placed on top of the pile, it is the first one to be given attention by the librarian. So again, for the first element, it pertains to the input process. So we have the Poisson arrival process, hence Markovian or letter M we used. For the second element, we have varied the service system distribution, and it pertains to the time the librarian returns the book to the bookshelves. That is Erlang distributed. Hence, we can use E sub k. For the third element, the number of servers we assume as librarian is 1. For the fourth element, instead of first come first serve, we have here last come first serve, because in the problem, it states that the last student who returned the book will be piled on the top. Hence, we use LCFS. For the fifth element, we have infinity because there is no restriction in returning books, and for the last element, we also have infinity. The Kendall-Lee notation for this is summarized as M E sub k1 LCFS infinity infinity. That's all my report, and for the continuation of this topic, the next reporter will be Miss Imas.
Good day everyone, I am Aiden J. Imas and I am here to discuss with you the sets of performance measure in the queuing system as well as the birth and death model of Markovian. So now let's proceed to the sets of performance metrics in the queuing system. So in here, I will just basically give you the sets of performance measure that we will monitor in the queuing system. So actually we have 4 sets, and the first set that we have is the Ls that represents the length of queue. Yan. So in here we have the LS that represents the average number of customers being served. Second is the LQ that represents the average length of customers in the line. And lastly, L is equals to LS plus LQ that represents the average number of customers in the system. And the second set that we have is the W's. Yan. In here we have WS that represents the average service time of a customers. Second is the WQ that pertains to average waiting time of customers in the line. And lastly is W is equals to WS plus WQ that represents the average waiting time of customers in the system. The third performance measure that we have is the probability of bulking. So bulking happens when a customer decided not to enter the line or the waiting line because it is either full or too long. So when we have a high probability of bulking, it will lead to loss of revenue or loss of customers' goodwill. And the last performance measure that we have is the server utilization. It is the proportion of time that a given server is busy as it attends to customers. And that is all about the sets of performance metrics in the queuing system. Now, I will also give to you the formula for L. Let P sub n steady state probability that the queuing system has n customers, which is L is equals to summation of n P sub n for all n, and it is basically the definition of average. Another formula is the LQ is equals to summation of n minus s P sub n for n is greater than s, where n minus s represents the number of customers currently in queue. And additionally, another important result na hinahanap sa queuing system is makikita sa Little's Law. So what is Little's Law? It is a theorem that determines the average number of customers in the queuing system based on the entry rate of the customers and average waiting time na ina-spend ng customers sa system. And it is mathematically expressed through the following equation. L is equals to lambda average times W, and the lambda average represents the number of arrival rate of customers in the system. And with the help of this little law, we can now relate the 4 major performance measure in the queuing system. Now let's proceed to the birth and death model of Markovian. In here, the state transitions are only 2 types, which is the birth and death, where birth increased the state variable by 1 and death decreased the birth by 1. Birth is the arrival of the customers in the system, while the death happens when a customer leaves the system, usually when the service is completed. So now, I will present Sir Pani's explanation for your further understanding.
From the general birth and death model, the steady-state probabilities can be computed as follows. P naught, or the probability that the system is empty, is equal to the reciprocal of 1 plus lambda naught over mu 1 plus lambda naught lambda 1 over mu 1 mu 2 plus lambda naught lambda 1 lambda 2 over mu 1 mu 2 mu 3. I hope you're getting the pattern. Plus lambda naught lambda 1 lambda 2 lambda 3 over mu1, mu2, mu3, mu4, and so on. P1 is equal to lambda naught over mu1 p naught. P2 is equal to lambda naught lambda 1 over mu1 mu2 p naught, or lambda 1 over mu2 times P1. P3 is equal to lambda naught lambda 1 lambda 2 over mu1 mu2 mu3 p naught, or lambda 2 over mu3 times P2. P4 is equal to lambda naught lambda 1 lambda 2 lambda 3 over mu1 mu2 mu3 mu4 p naught, or lambda 3 over mu4 P3. P5 is equal to lambda naught lambda 1 lambda 2 lambda 3 lambda 4 all over mu1 mu2 mu3 mu4 and mu5 p naught. That is also equal to lambda 4 over mu5 times P4. For those with background in continuous time Markov chains, these formulas are rooted from rate in equals rate out concept exhibited by Markov chains in the steady state. Some of the queuing formulas we will encounter later are derived using the formulas of P sub n's in combination with the definition of the performance measures and Little's law. We are now ready to answer an example. Consider the rate diagram of a Markovian queuing system. Find the steady state probabilities P sub n's. Arrival is constant at 5 per hour except when there are already 5 customers in the system. No more customers arrive at this point. The system therefore has a finite number of states. Death rate is 4 per hour when n equals 1 and 8 per hour when n is greater than or equal to 2. Presented are the computation of P sub n's following the formulas discussed earlier. P naught again is equal to the reciprocal of 1 plus 5 fourths plus 5 times 5 over 4 times 8 plus 5 times 5 plus 5 divided by 4 times 8 times 8 plus dot dot dot. P naught is equal to 0.249. P1 is 5 fourths of 0.249, that is equal to 0.311. P2 is equal to 5 over 8 times 0.311, the value is 0.195. P3 is equal to 5/8 of 0.195, the value is 0.122. P4 is 5/8 of 0.122 with a value of 0.076. Lastly, P5 is 5/8 of 0.076 with a value of 0.048. We will later see that this shortcut approach can be used to compute performance of queuing systems with finite states.
Let us now discuss the first queuing model and one of the most basic models, MM1. MM1 is a Markovian queuing model with a single server. Note here that the arrival process is Poisson and the service time is exponential. MM1 example deals with a queue in the cashier of a grocery store, which has one waiting line and one server. MM1 queuing system means we have one queue per server, but it doesn't mean that you cannot have multiple servers. You can have 3 servers with 3 queues and each of the servers is computed using MM1 model. So before tayo mag-proceed sa mga example ng MM1, alamin muna natin yung formulas and symbols na dapat natin tandaan. Lambda is the arrival rate of the system, mu is the capacity of the system, rho is the probability that all the servers are in use, L or the average length of the queuing system or the average number of customers in the queuing system, P naught, the probability that the queuing system is empty, W and WQ or the waiting time or the average waiting time of customer in queue and in the system. Lambda corresponds to the arrival rate, while mu corresponds to the service rate. Here are the formulas to get the probability that all the servers are in use, to get the probability that the queuing system is empty, to get the probability that there are customers in the system, the average length or the average number of customers in the queuing system, the waiting time or the average waiting time of customer in queue. A regional airport has a single runway. Airplanes requiring the use of the runway arrived at a Poisson rate of 12 per hour. Each plane uses the runway for an exponential time with mean of 4 minutes. for the first question, to find the average waiting time of airplanes before they can use the runway, the formula is WQ equals lambda over mu times mu minus lambda. Our lambda is 12, while our mu is 15. 12 over 15 times the total of 15 minus 12 is equal to 0.2667 hour or 16 minutes. So the average waiting time of airplanes before they can use the runway is 16 minutes. Next question, what is the utilization of the runway? The formula is rho equals lambda over mu. Our lambda is 12, while our mu is 15. 12 over 15 is equal to 0.80. Next question, to compute the average number of airplanes currently using or waiting to use the runway, the formula is L equals lambda over mu minus lambda. Our lambda is 12, while our mu is 15. 12 over 15 minus 12 is equal to 4 planes. So, the number of 4 planes are currently using or waiting to use the runway. Lastly, to find the probability that an airplane doesn't need to queue to use the runway, P naught equals 1 minus rho equals 1 minus 0.80, which is the utilization, equals 0.20. Students arrive at the head office of Universal Teacher Publications according to a Busan input process with a mean rate of 40 per hour. The time required to serve a student has an exponential distribution with a mean of 50 per hour. Assume that the students are served by a single individual. Find the average waiting time of a student. Given that the lambda is 40 per hour and mu is 50 per hour, the formula for the average waiting time is WQ equals lambda over mu times the total of mu minus lambda. Our lambda is 40 and our mu is 50. 40 over 50 times 50 minus 40 is equal to 4.8 minutes. So, the average waiting time of a student before receiving service is 4.8 minutes. Universal Bank is considering opening a drive-in window for customer service. Management estimates that customers will arrive at a rate of 15 per hour. The teller, whom it is considering to staff the window, can service customers at the rate of 1 every 3 minutes. To get the average number of customers in the waiting line, the formula is LQ equals lambda squared over mu times mu minus lambda. Our lambda is 15 and our mu is 20. So 15 squared over 20 times 20 minus 15 is equal to 2.25 customers. Next, to get the average number in the system, the formula is L equals lambda over mu minus lambda. Our lambda is 15 and our mu is 20. 15 over 20 minus 15 is equal to 3 customers. 3 customers are in the system. Next, to get the average waiting time in line, the formula is WQ equals lambda over mu times the total of mu minus lambda. 15 over 20 times 20 minus 15 is equal to 0.15 hours. Lastly, to get the average waiting time in the system, the formula is W equals 1 over mu minus lambda. Our lambda is 15 and our mu is 20. 1 over 20 minus 15 is equal to 0.20 hours. So, the average waiting time in line is 0.15 hours and the average waiting time in the system is 0.20 hours.
That's all for MM1Q.
Next is the MMS queuing model. It is when we have a single queue with more than one parallel servers. In MMS, the arrival distribution of customers must follow Poisson distribution, and the distribution for service time must follow exponential distribution, with S as the number of parallel servers, lambda as the arrival rate, and mu as the service rate. In the output, LQ is the average number of customer in waiting line for service, L is the average number of customer in the system, while WQ is the average time a customer spends in waiting line and waiting for service, and W is the average time a customer spends in the system. Here is an example. To compute for the performance measures, we first need to compute the other figures.
In this problem, a clinic has 3 dentists. Since there are 3 dentists, this problem is MMS with S equals to 3. Then it also says that the arrival of patients is Poisson distributed with mean of 4.8 patients per hour. And it also says that the time a dentist needs to serve a patient is exponentially distributed with mean of 25 minutes. Thus, lambda is equals to 4.8 patients per 1 hour and mu is equals to 1 patient per 25 minutes. And as you can see, our mu is not converted into an hour. So we still need to compute for it by dividing 60 minutes, which is equivalent to 1 hour, into 25 minutes and multiplying it by 1, so that we can get our new mu, and that is 2.4 patients per 1 hour. Then, we can now compute for queuing utilization using this formula, and the result is 0.667. Next is compute for the probability that the system is empty given by this formula. And the answer is 0.111. Finally, using these figures, we can now compute for the probability that all servers are busy. The computed value is 0.444. After computing this, we can now determine the values of LQ, L, WQ, and W. Just simply substitute the values of variables required in the formulas. The result in LQ is 0.889 patients. That means that on the average, there are about 0.889 patients in the waiting line for service. Then, to compute for L, take note that we need to substitute the value of LQ to the formula of L, and we compute the final value of 2.889 patients in the system. Next, the average time a patient spends in waiting line before it is served by dentists is 0.185 hour, equivalent to 11.1 minutes. Lastly, to compute for W, we also substitute the value of WQ to the formula of W, and we compute the final value of 0.602 hour, equivalent to 36.12 minutes, and that is the average time a patient spends in the system in the problem.
So we are now proceed to my topic, which is the GG Infinity or the self-service model. So this queue model only happens when the customer is also the server. So the number of servers in this kind of queue model has the infinity number of servers. So to further understand this GG Infinity model or the self-service model, let's utilize the candle Lee notation by examining each of its elements. So for the first element, it represents the inter-arrival time of the customer, which is the general distribution. And then for the next element, it's the service time. We have the general distribution as well. And then for the third element is the number of service, which is infinity, which means there is no limitation on the number of services that are available. And GJ Infinity indicates that as the customer comes to the system, they can immediately go to any service and start the service process. So in this queue model, it shows that the customers never has to wait for the service to begin because once they arrive in the system, they can immediately serve themselves. And this is why it is also called the self-service model. So now let's take a look for its equation, which is WQ equals LQ equals 0. So WQ stands for the average waiting time of customers in the line, while LQ is the average length of customers in the line or queue, and 0 meaning there is no waiting time or length of customers in the line. Also, we have W equals 1 over mu. That stands for service time reciprocal to service rate. We will be using this when we are going to solve for the expected interval time. And then next, for L equals to lambda over mu. It is applicable to any GG infinity models, and we are going to use it when we have to solve to average number of customers in our queuing system. But how about when the inter-arrival time is exponentially distributed? So through Kendall notation, this is how it looks like: mg, infinity, and so on and so forth. So for the first element, the inter-arrival time, we have Markovian since it is exponentially distributed. And for the second element, we have the service time, which is generally distributed. And for the third element, the number of service is infinite. So meaning there is no limitation on the number of service that can enter the system. So in this case, if the inter-arrival time of system is exponentially distributed, this would be the queue model system that we have to deal with. And for its formula, we have the steady state probability. So let P sub n is equal to A to the negative lambda over mu times lambda over mu raised to n over n factorial. So the P is to calculate the suggest probabilities in the system, and n as the number of entities or customers in the system, and lambda is the arrival rate of the customer, and lastly the mu as the service rate of the queuing system. So for example, on average, 3 ice cream shops open in a town each year, and on average, each shop stays in town for 10 years. The first problem: what is the average number of shops in this town in year 2025? And for the next problem, if the time between opening of the shop has exponential distribution, what is the probability of having 25 shops in this town in a year? Let's start with reviewing the characteristic of this system through the help of Kendall notation. So first, let's determine what is queue system and the customers in this problem. So first, the town would be the queue system, and the ice cream shops are the customers or entities that enter the system. And as given the problem, there are 3 ice cream shops that open in a town each year, and each of them stays for only 10 years. So the 3 ice cream shops would be the arrival time, hence lambda is equals to 3 shops of ice cream each year, and mu, which is the service rate over service time, it is 1 over 10 since 10 years the indication that the ice cream shop would close and leave the system. So it's shown that the service time will be the years that they will stay in the town. And for the number of servers, it shows that there is no limitation on how many servers can enter the system. Therefore, it falls under the category of infinite service type of queuing system. However, the question is, what is the average number of shops in this town in year 2025? So 2025 can also mean in the long run. So we will be using L is equals to lambda over mu, and let's try to substitute those given that we analyzed. So lambda is 3 shops of ice cream each year, and mu is the service rate over service time, which is 1 over 10. So if we calculate this, it will give an answer of 30 shops that are working in this town by year 2025 or in the long run. For the second problem, if the time between opening of the shop has exponential distribution, what is the probability of having 25 shops in this town in a year? So stated that it is exponentially distributed, and we are looking for probability that 25 shops are working in this town in a year. So obviously, as we discussed, this is where mg infinity happens, as the inter-arrival time is Markovian or exponentially distributed, and the service time is generally distributed, and it also have the infinite server. So we will be using the steady state probability to calculate the probability of 20 shops in a year that is working in this town. So we have P sub n is equal to E to the negative lambda over mu times lambda over mu raised to n over n factorial. So once again, let's substitute all the given to the formula. N is equals to 25, and for the lambda, we have 3 shops, and for the mu, once again, we have the service rate over service time, which is 1 over 10. So as we calculate this probability, it will give an answer of 0.05. Hence, there are 5% of chance that there are 25 shops working in this town in any given year. So I hope you learned something about the GG Infinity or the self-service model, and that will be all for my topic.
So another queuing model is the MMS GDK Infinity. This queuing model has a limited system capacity. So sa model na ito, since limited ang capacity ng system, hindi lahat maa-accommodate or can enter the system. Unlike sa ibang models, customers are assumed to enter the system. And next, the probability of bulking is non-zero. So what is bulking? Bulking happens when a customer cannot or refuses to enter the line because it is either full or too long. So yung customers, they decide either not to join or they cannot join dahil either mahaba na yung pila or wala ng space para pumila. So therefore, the cost of losing customers here in this model is present. So it is assumed nga na hindi lahat makaka-enter sa system because there are certain limitations. First is physical limitation, meaning there is limited space for customers to queue. And second, it can be the customer behavior, where customers prefer not to wait. So one example could be a queue in a drive-thru. So physical limitation is present since there are limited space for the vehicles, therefore giving them a limited capacity to enter the system. So some of the customers cannot join, and as well as the customer behavior, since sometimes some customers decide not to join or wait the queue since it's too long dahil minsan medyo matagal din mag-take ng orders sa drive-thru sa mga fast foods. And another example can be in videoke booths in an amusement arcade or simply in a car wash facility. Diba, it can only cater limited customers. So yung ibang customers, they don't want to wait. Therefore, they tend to leave and find another without even joining the queuing system. So yun yung concept ng model na to. The MMS GDK Infinity has a limited system capacity. Therefore, hindi lahat nakaka-join sa queue or even sa system dahil first, physical limitation, meaning onti lang yung space for queuing, and second, customer behavior, hindi nila kaya maghintay, therefore they leave or they not join the queue. So before tayo mag-proceed sa problem, let's tackle first the 6 elements of this queuing model. So the first M is the Markovian arrival rate of customers, which is denoted by lambda. The second M is the Markovian service time of each server, which is denoted by mu. Then S is the number of servers in the facility. Like for example, in a drive-thru, may isang server. So 1 ang ilalagay sa S. Then GD, stands for general discipline, which it determines which customer will be served next. So normally in this model, it is a first come first served basis. Then K is the system capacity, which it determines the maximum number of customers that may enter the system. So, sa example kanina, sa drive-thru, sa isang server, ang system capacity is let's say 6. So, 6 ang ilalagay. Then last is infinity. It is the calling population or the potential customers. So, infinite siya because it has a large population and the rate of arrival of customers is not affected by the number of customers that have already joined the queuing system. So, as is siya, wala siyang equivalent na number. So, let's have an example. Our example has a single channel queuing model. These are the assumptions. First, arrival rate is known and constant. Second, arrival rate follows Poisson distribution. Third, service rate is known and constant. Fourth, service rate follows exponential distribution. Fifth, arrivals are patient. Sixth, arrivals are served on first in first out basis. And last, service rate is greater than arrival rate. And these are the equations to be used to each question. And take note that customers in the system refers to the customers who are waiting and customers who are getting the service. And the customers in the queue refers to the customers who are waiting only. So let's proceed to the problem. A man's barber shop has one barber named Raju. Since the shop has only one barber, therefore it is a single channel queuing model, so S is equals to 1. Then it says that customers arrive at the shop at the rate of 2 per hour and Raju takes 15 minutes to perform a haircut. So if we put it into the equation, it is lambda equals to 2 customers per hour since that is our arrival rate, and mu is equals to 1 haircut per 15 minutes since that is our service time per server. Then equate 15 minutes to 60 minutes to make it 1 hour. So we multiply it by 4, then we also multiply 1 by 4, so our mu becomes 4 haircuts for 1 hour. So now we calculate these questions by using our formulas earlier. First is the average number of customers at the shop. Second, the average number of customers waiting for a haircut. Third, the average time a customer spends at the shop. Fourth, the average time a customer spends waiting before getting a haircut. And fifth, the probability that Raju is free. So first is the average number of customers at the shop. Our equation is L is equals to lambda over mu minus lambda. So it is 2 divided by 4 minus 2 equals 1, or 1 customer at the shop. Second, the average number of customers waiting for a haircut. Our equation is L sub Q is equals to lambda squared over mu times mu minus lambda. So it is 2 squared divided by 4 times 4 minus 2 equals 1 over 2, or 1 customer waiting for a haircut. Third, the average time a customer spends at the shop. Our equation is W equals 1 over mu minus lambda. So it is 1 divided by 4 minus 2 equals 1.5 hour, or 30 minutes a customer spends at the shop. Fourth, the average time a customer spends waiting before getting a haircut. Our equation is W sub Q equals lambda over mu times mu minus lambda. So it is 2 divided by 4 times 4 minus 2 equals 1/4 hour, or 15 minutes a customer spends before getting a haircut. And fifth, the probability that Raju is free. Our equation is P sub O equals 1 minus lambda over mu. So it is 1 minus 2 over 4 equals 1/2, or 0.5 probability that Raju is free. Therefore, it is impossible that there is no customer in the system.
The next model is MMSGDNN model. This queuing system assumes that the input populations is finite. This means that the numbers of customers that can enter the systems is limited. In the first example, the 5 machines that require setup act as the customers in the queuing systems with the employee as the server. The example also highlights how the model got its alternative name, machine repair model, noting that the example can be modified, such as repair is performed on the machine instead of setup. The next queuing models involve systems with finite calling population. One peculiarity of this model is related to lambda. Lambda is in the queuing model represents the arrival rate of individual customers, whereas in the previous models, lambda is aggregated arrival rate of all customers. Presented here is the corresponding rate diagram for the MM1, GD, and N queuing model, and the applicable formulas for this model. Presented next are in the formulas and rate diagram for the MM, GD, and N model. We will use the succeeding examples to explain the elements of the rate diagrams. For the first example, a printing business has 5 printing machines used for the high volume orders. All throughout the day, these machines are running except for a few times when they are required to be attended by a printing employee to set up the machine parameters. In some instances, the machines may wait for an employee to be available since the employees may be attending another machines for setup, the business employees to printing employees. Each employee can set up a machine at an exponential time with the mean of 20 minutes. After setup, each machine runs for an exponential time with the mean of 2 hours before requiring another setup. So, let's draw the rate diagram of these queuing models. So, we model the machine as our customers and we model the technicians as the servers. We model the machines as our customers and we model the technicians as the servers of this queuing system. Let's consider the value of the breed plates in the problem. Each machine takes 2 hours before needing technician's attentions or equivalent or rate of 0.5 per hour. It is emphasized that this rate is for each individual machine. Now, let's refer to state 0. It means no machine is in the viewing system as all are working, all 5 of them. However, have a read of 0.5 and effect the rate before one of these machines needs the technician's attention is 5 times 0.5 or 2.5 per hour. This explains the 2.5 per hour rate from state 0 to state 1. For state 1, one is already being set up but form eventually requires service. Hence, an effective rate of 4 times 0.5 or 2 per hour is applicable. Same computations apply to other states. For the death rates, this corresponds to rings of finishing setup adjusted based on the number of technicians working. For example, when there is one technician, busy rate is 3 per hour corresponding to the 20-minute setup time, but when 2 technicians are working separately, the death rate is 6 per hour. That is 2 times 3 per hour. 2 times 3 per hour. This explains the rates in the rate diagram of this queuing model. This queuing model has Kendall-Lee notations of MM at 2 FCFS 55 with the individual arrival rate of 0.5 per hour and service rate of 3 per hour. So for the first questions in this problem, what is the proportion time that both employees are either as machines are working? So to answer the question, the corresponding performance measured to this P or the probability that the viewing system is empty, using the formulas available, we computed that the probability that the queuing system is empty is 456. For the second problem, on the average, how long does the machine queue before being attended by a technician for a setup? We will be using little slow to get the value of WQ, which is required performance measures for this problem. WQ is equal to LQ, all overlap the average. Before we can get LQ and lambda average, we need to compute first the steady state probabilities. So, we computed test steady state probabilities
P1 up to P5 on the top of the probability earlier computed. Afterward, we computed LQ based on its definitions. The value of L is then computed based on an available formula. After getting the value of lambda, average is computed before eventually getting the final value of WQ, which is roughly 1.23 minutes. These computations are based strictly on the formulas available to demonstrate their usefulness. However, there are other shorter computations available. For the last question, for this item, a cost of 1,000 per hour is incurred if the machines is not running due to lost machines productivity. Find the total expected cost of the waiting per hour considering all the machines. The waiting cost is computed as 1,000 times W times lambda average. W is the non-productive time when every machine requires a technician service. 1,000 is the cost per non-productive hour. We still multiply these terms by lambda average because the number of machines requiring service is the technicians in an hour is lambda average. This gives us an early non-productive cost of 751 pesos.
So now let's discuss the MG1 queuing model.
So what is MGI queuing model? So it is a queue model where arrivals are Markovian, modulated by a Poisson process. Service times have a general distribution and there is a single server. So Markovian queues or those with an exponential interval arrival time and service time are studied more widely because of it top ability of exponential or Markovian queues. So MGI queuing model kinukonsider siya na widely used because it uses exponential distribution wherein it calculates the time elapsed between the events. So the model name is written in Kendall's notion and is an extension of the MMI queue where service times must be exponentially distributed. So as I mentioned earlier, ginagamit niya yung exponentially distributed. And one of the benefit of MGI queuing model is that, for example, in a bank transaction, because of customers na kada minute or kada oras is nag-a-arrive, no? And then meron lang limited na server doon sa isang bank, kapag ka hindi siya na-manage ng maayos, pwedeng maapektuhan yung service nila dun sa kanilang clients. So, that's why MQA model is a helpful tool to ensure na masaserve nila quickly and efficiently and respond to the demands in timely and cost-efficient fashion dun sa kanilang mga clients. So, how to calculate the MGI QE model? So, ginagamit yung Pulaschik-Kenchin to calculate the MGI QE model and also to evaluate the performance of the system. So, as we can see, merong apat na formula under the Pulaschik-Kenchin formula. So, the first one is the LQ. So, this is used to calculate the average number of customers in the line. So, LQ is equals to the lambda sigma squared plus lambda over mu squared divided by 2 times 1 minus lambda over mu. So, next is the WQ. So, WQ used to calculate the average time spent in line. So, to calculate the WQ, we can use this formula. So, WQ is equals to the average number of customers in the line over the lambda. So, next is the W. So, W represents the average time spent in the system. So, we can use this to calculate the average time spent in the system. And the formula is W is equals to the average time spent in the line plus 1 over the mu. So lastly, we can also use this formula to calculate the average number of customers in the system. So we can use the formula L is equals to lambda times the average time spent in the system. So next, let's talk about the properties or dun sa mga sign na nakita natin dun sa formulas ng model MGI Queen model. So para mas lalo nating maintindihan kung ano-ano ba yung mga sign na nandun. So first is the lambda. So lambda, it represents the arrival rate. And then the mu, this is the service rate per server. And then the sigma squared is the variance of the service time. And then the LQ, it represents the average number of customers in the line. So WQ, this is the average time spent in line. W, average time spent in the system. And L, average number of customers in the system. So, para mas lalo nating maintindihan kung paano ba yung process ng pag-calculate ng MGI Queen model, I prepare a 2 example. So, first problem. So, Janica arrived at AB Bank according to exponential distribution with a mean rate of 20 per hour. The time required of the bank to serve the client is 0.005 per hour with an average rate per server of 30 per hour. Compute for the LQ, which means the average number of customers in the line, WQ, which is the average time spent in line, W, the average time spent in the system, and L, the average number of customers in the system using the Polaczyk-Ching formula. So, to calculate that, first we need to identify the average number of customers in the line kasi ito yung pinaka-basis para din makalculate yung other problem na hinahanap. So, first, we can use this formula. LQ is equals to lambda sigma squared plus lambda over mu squared divided by 2 times 1 minus lambda over mu. So first, we need to identify the variable doon sa problem. So, ang pinaka top 3 important variable na kailangan nating mahanap sa given problem ay yung lambda, yung mu, and then yung variance. So, sa given example, balikan natin. So, first hanapin muna natin yung lambda. So, from here, it says that Janica arrived at AB Bank according to the exponential distribution with a mean rate of 20 R. So, as we can see, ito na yung pinaka-clue para makita natin agad yung lambda. So, arrived at the bank according to exponential distribution with a mean rate of 20 R per hour. So, this is the lambda. So, next, hanapin naman natin yung mu. Wait. Hanapin naman natin yung mu. So, yung mu, ito yung service rate per server. So, the time required of the bank to serve the client is 0.005 per hour with an average rate per server of 30 per hour. So, ang clue dito is yung average rate per server. So, yung mu natin is 30. Lastly, hanapin naman natin yung variance. This is the service time. So, variance, so since from the given problem, the time required of the bank to serve the client is 0.005 per hour. So, it means na ito yung variance, service times. So, going back dun sa problem, so ayan, so since we already identify yung important variable nitong given problem, we can now proceed to calculate the MGI Queen model using the first formula, which is the average number of customers in line. So, step 1, so we need to, syempre, distribute muna yung mga variables na nahanap natin dun sa formula. So, LQ is equals to lambda, which is 20, ayan, 20, times the variance, which is 0.005 per hour, ayan, squared plus lambda, again, which is 20, ayan, 20, and then the mu, which is 30. So, squared, ayan, over 2 times 1 minus lambda, which is 20, over mu, which is 30. So, next step is, kailangan nating i-follow yung PEMDAS rule. So, according to PEMDAS rule, we need to first calculate yung equation na may exponent, which is itong numerator. So, first, when we say exponent dun sa equation, ibig sabihin nito, kinakailangan mong i-multiply yung variable by itself. So, from here, dito sa 2 equation na to, so 20, no, times 20. Kasi, ang exponent niya is 2. So, 20 times 20 is 400. So, same thing with 0.005 times 0.005 is equals to 0.00025. So, you can use calculator and check if my calculation is right. So, next, the second equation. So, plus, since 2 rin dito yung exponent, so, we should multiply the variable by itself. So, 20 times 20 is equals to 400 over 30. So, 30 times 30 is 900. So, next. So, hindi pa dyan natatapos. So, meron pang denominator. So, 2. So, according to PEMDAS rule, so, we need to calculate first yung merong parenthesis sa loob. So, ano yon? Ayun yung 20 over 30. So, since ito yung nasa pinakaloob ng parenthesis. So, 20 divided by 30 is equals to 0.67. So, yan. So, ayan muna. Yan muna yung step 2 natin para hindi tayo masyadong malito. So, stop muna tayo dyan for the step 2. And now, let's proceed with step 3. So, sa step 3, ngayon, isi-resolve naman natin yung numerator. So, 40 times 0.00025 is equals to 0.01. So, kindly use your calculator then. Kumuha kayo ng calculator to solve this problem. So, para ma-check nyo rin if tama. Plus, 400 divided by 900. So, it is equals to 0.44. So, over, yan. So, now, let's minus the 1 dito sa 0.67. So, 1 minus 0.67 is equals to 0.33. So, ayan. So, copy lang natin yung 2. Ayan. Then, now, let's proceed with step 4. So, ayan. So, para makuha natin yung final answer, we need to add, syempre, itong numerator. So, 0.01 plus 0.44 is equals to 0.45. And then, the denominator naman, we need to multiply. So, 2 times 0.33 is equals to 0.66. So, now, we need to divide. So, divide this 0.45 to 0.66. So, it's equals to 0.682. So, therefore, the average number of customers in the line is 0.682. So, hindi pa dyan natatapos yung solution natin. So, we need also to identify the average time spent in line. So, to calculate that, we can use this formula. So, WQ is equals to the average number of customers in the line over the lambda. So, first, kagaya ng ginawa natin kaginina, we need to identify the variable doon sa given problem. And the average number of customers in the line is also given na since we already calculated it doon sa nauna nating computation. And then, the lambda, based doon sa given problem, is 20 per hour. So, since we already identified the important variable, we can now proceed to calculate it based on the formula. So now, WQ is equals to 0.682 over 20. So, kapag dinivide natin yan, ang kalalabasan ay 0.034. So, therefore, the average number of customers in line is 0.034. So, next, we need to calculate the average time spent in the system. So, to calculate that, we can use this formula. So, W is equals to the average time spent in line plus 1 over mu. So, kagaya ng ginawa natin kanina, we need to identify the important variable. So, the WQ or the average time spent in line is already given based doon sa kinumpute natin kanina. Ayan. Ayan. So, yan. So, the average time spent in line is 0.034 and the mu is 30 per hour. So, now, we can now distribute this variable dito sa formula. So, now, W is equals to 0.034 plus 1 over 30. So, based on the PEMDAS rule, kinakailangan muna natin syempre i-divide itong 1 over 30. So, 1 over 30 is equals to 0.33. And now, we can now add the 0.034 and then the answer is 0.364. So, therefore, the average time spent in the system is 0.364 per hour. Lastly, so last computation is the average number of customers in the system. So to calculate that, we can use this formula. So L is equals to the lambda times the average time spent in the system. So first thing first, we need to identify the important variable. So W is equals to 0.364 per hour. So ayun yung na-calculate natin kanina dito. So yan, 0.364 per hour. And then the lambda is 20 per hour. So distribute this variable dito sa formula. So L is equals to 20 times 0.364 and then the answer is 7.28. So therefore, the average number of customers in the system is 7.28. So that's all. Thank you for listening. I hope na naintindihan niyo yung process on how to calculate the MG1 queuing model.
We are now moving on to the final set of examples for our queuing theory lesson. This model lacks a specific Kendall-Lee notation, which has a 6-element classification method for categorizing queuing system. The first involves cooperating servers. This metric measures the performance of a system in which servers can assist one another when there are just a few customers available to be served. The second takes into account bulking, in which the arrival rate of customers entering the system is determined by the number of customers currently inside the system. These two models are sophisticated and can be skipped if desired. However, these two examples show how birth and death analysis of Markovian queues can be used to evaluate the systems. To help you better understand the concept of other models, I will present you Professor Angelo Ani's explanation, which contains formulas, examples, and instructions on how to compute and apply them.
Our first example tackles the cooperation among servers. A car wash shop has 3 employees. Each employee can wash a car in an exponential time with mean of 45 minutes. However, when there are only 2 cars in the shop, one of the employees will help one of the other 2, reducing the average time from 45 minutes to 30 minutes. Meanwhile, the customer being served by one employee will still have a service time average of 45 minutes. Note that when a new vehicle arrives, one of the cooperating employee will leave its partner and will now assist the newly arrived customer. In that case, service time average goes back to 45 minutes per customer. If there is a single customer in the shop, only 2 employees will wash the vehicle, with a service time average of 30 minutes. The third employee will be idle during this time. Cars arrive to this system at a Poisson rate of 5 customers per hour. However, customers bulk when 2 cars are already waiting in the shop, excluding those being washed. In order to solve the accompanying questions, the rate diagram of this queuing system must be constructed. Arrival rates are at 5 cars per hour except when there are 5 cars in the shop. These are modeled in the birth rates of the rate diagram. When there is a single car in the shop, service time is 30 minutes or equivalently a service rate of 2 per hour. If there are 2 cars in the shop, one is served at a rate of 2 per hour and the other is served at a rate of 1.33 per hour. If there are 3 or more cars in the system, each is served at a rate of 1.33 per hour or an aggregated total of 1.33 times 3, which is 4 per hour. The steady-state probabilities are solved using the birth and death shortcut. We are now ready to solve the following questions. A. Find the expected revenue per hour of the shop if each vehicle washed generates 200 pesos. To answer this, we need to compute lambda average or the average number of cars that enter our system, excluding those that bulk. Lambda average is computed as the weighted average of the entry rates with 0 car entering when there are 5 cars already in the shop. Lambda average is 3.542 vehicles per hour. This represents the number of cars that enter the queuing system and are eventually served. Thus, hourly revenue is 200 times lambda average, which gives us a total of 708 pesos per hour. For the second question, we are asked to find the average number of vehicles present in the shop. This is given by the performance measure L, which is computed to be 3.349 using its definition formula. For the third question, on the average, how long does a vehicle stay in the car wash? This can be answered by computing W. W, using Little's law, is equal to 56.73 minutes. The last example to be discussed is a model that tackles bulking customers. A newly opened tea shop is very popular to mall goers. The Poisson arrivals of customers to the said shop has a rate of lambda equals 26 per hour. The shop has a single employee. The mean service time is 2.5 minutes. Assume that the service time is exponentially distributed. Though popular, some clients may not go inside when there is a relatively long queue. They will instead go to other tea shops in the mall. Specifically, an arriving customer will bulk with probability 0.3 if there are 3 or 4 customers inside, including the one being served. This probability of bulking goes up to 0.75 if there are 5 or 6 customers inside. No customer enters the queue when there are 7 customers. As we can see in the corresponding rate diagram, customers arrive at a rate of 26 per hour when there are at most customers in the shop. It is reduced to 18.2 for states 3 and 4 as 30% of customers bulk. This is further reduced to 6.5 per hour when there are 5 or 6 customers in the queuing system. No customer further enters if there are 7 customers. The steady-state probabilities are given, computed using the birth and death shortcut. Let's now answer the questions. For A, what is the probability that the employee is idle? So that is simply the probability that there is no customer in the queuing system, P0, and that is equal to 0.1544. For the second question, find the average waiting time before a customer is entertained by the employee. This is given by WQ. In order to compute WQ, we first compute LQ using its definition. We then compute lambda average using the weighted average of the arrival rates, before getting WQ using Little's law. The final value of WQ is 4.952 minutes. For the last question, How many customers are lost per hour due to bulking? Lambda bulk is the difference of lambda and lambda average. Lambda is the rate of customers trying to enter the tea shop, while lambda average represents those who actually entered. The rest would be the bulking customers. With this example, we're done covering some of the basic queuing models. That ends our module on queuing theory. Thank you.
To summarize, queuing theory is an important tool for studying and managing systems that involve waiting lines. It can help to optimize system performance and also allocate resources efficiently. Since results of queuing theory formulas are valid only when the assumptions of the models are met, one must take action not to haphazardly use a model without checking the validity of necessary assumptions. Indeed, the rigorous requirements of this model somehow limit their applications in real life. If situations do not perfectly follow the conditions of model, one may opt to use simulation to evaluate the system performance. Knowledge in queuing theory helps in estimating effects of operational decisions, such as increasing number of servers, improving service times, provision of additional queuing spaces, and reducing variability of service time, perhaps automating the service. It is emphasized that the values of the performance metrics serve as basis or guidelines in making decisions towards the improvement of the associated operation or process. These values can be used also to compare the performance of two different queuing systems. In a customer-facing environment, effective queuing systems are crucial. From a safety perspective, poor queuing systems can lead to overcrowding and, in light of COVID-19, unnecessary contact between customers. From an operational perspective, pure queuing systems can lead to a drop in productivity from staff as they spend time trying to organize the queue. From a monetary perspective, if customers decide to leave the queue or are put off from even joining, this leads to a loss of profits. Queuing theory influences the design of efficient and cost-effective workflow systems from a commercial standpoint.